My name is Ezequiel Gutesman, and I work at Core. And I'm about to present a work we made with Ariel Futoransky and Ariel Weisbein. And, well, let's start. In this talk, we'll talk about mainly a protection to protect web applications against injection attacks and enhance privacy. And the talk will be organized. We'll first make a brief introduction. Then we'll talk about known tools to address injection problems. Then we'll present the classical taint mode, and that kind of motivates our work. And then we'll compare it with character granularity information. Then we'll introduce our project called Core Grasp, and then we'll talk about future work. So maybe some of you are familiar with the things I'm talking in the introduction, so I ask you to be patient. Maybe some of you are not. So we're talking about injection attacks and why we will have to be worried about them, and the objectives and results, the objectives that motivated our work. They will start a demo that will be running while the presentation goes on, describe the threats and the countermeasures that are known. So every day, injection vulnerabilities are discovered. So most of the exploits that exploit these vulnerabilities make use of these weaknesses, and the exploitation of these vulnerabilities can lead to different threats. For example, data theft and alteration, impersonation, also remote code execution in clients' browsers. So one of the problems is that as programming languages evolve, and while they'll lower the curve for new programmers to start developing web applications, at the same time they fail in introducing mechanisms to prevent injection attacks. And you also can find that privacy can be compromised through these attacks, and we need some policies to protect them. So which were the objectives of our work? We wanted to develop a technique so that it protects all web applications without requiring to modify their source code, and neither major changes to its network architecture. So injection attacks must be detected and may optionally be blocked. This should be configurable. And it also must allow the owner of the web application to define policies over data. And this system must enhance privacy over this data. So one important aspect of these objectives is that if we want to detect and block injection attacks, we must be very accurate. Otherwise, we will fall into a big amount of false positives. So we don't want it. So what we design is a technique which allows us to detect injection attacks and also privacy violations, which is called GRASP. And we've been working on this for a few years now. We have a prototype for PHP, which is called GRASP for PHP, and that we are releasing today as an open source software. So to illustrate a simple SQL injection example, we have a login. So a user comes into our website and logs in, typing his username and his password, and later this goes into the web server, and it's used to query a database management system. And well, maybe this is a very simple query, but it will do well for our example. So the values then the user entered are concatenated into the query and used to authenticate it, to authenticate the user. But what will happen if the user enters something different than a regular username? For example, a very common way to illustrate SQL injections are adding some tautologies to the word clauses, modifying the query, so it will always hold the condition, and any user could authenticate. So now we're going to do a demo about our work. So we have two copies of the same PHP version. One of these is patched with our solution. We'll first install the original copy of PHP, and then we'll test a public exploit against a popular CMS. This exploit exploits a blind SQL injection, which is a SQL injection which we cannot see the output, but we know we have the possibility to execute our own code. As a result, this exploit retrieves the administrator password of the website. Then we will test the same exploit, but with Grasp enabled, and we'll see what happens. So maybe I'll switch notebooks, see if it works. Okay. So we'll now install the original PHP into the server. I have already compiled it because it will take some time. So we restart the Apache server. And then I have the exploit takes as parameters the web server, which is a local host, the remote directory at the web server, and a valid username, a registered username, which is not required to be an administrator. So, So this will go over the database, retrieving one character at a time from the MD5 password hash of the administrator user. And well, at the end, we'll see the administrator username and the password, but we won't stay here looking at the screen until it finishes. We'll go back in a few minutes. So now it's retrieving one character at a time and telling us which character it is. So then we'll see the complete password. So the privacy threats we are facing are, well, applications handle private data from users. Sorry. And if we don't have policies to protect this data, this can lead to a privacy violation if this data is disclosed. So injection attacks can lead to this kind of privacy violation and will end at private data disclosure. So, I'll go back. So it's important to define privacy policies over the data and to enhance them. So I'll go quickly around, I will make a quick review about the most popular injection attacks. The first one is cross-site scripting, which happens when data originated from the user. It's stored, for example, in a database, and then it's output to the end user. So another user can suffer from this attack. For example, let's say I'm subscribed in a discussion forum, and as my username, I will enter this chain of characters, which in JavaScript are a simple alert, a pop-up. But think about if I post a response to a message and a user is reading my post, if my username is displayed, he will have a pop-up in his browser. But imagine this could be any JavaScript code. So This kind of attacks can happen in every web page that outputs data to a web user, all of them, okay? So we have to be aware of this kind of attacks. Another kind of injection attacks are shell command injections, which are similar to SQL injections, but this time the language used to execute a service behind the web application, it's a shell, for example. So let's say I upload the file to a web server, and as the file name, I enter this chain of characters, which are different Linux commands piped. So it will upload my file to the web server, and then it will erase the parent directory. Of course, we need to have permissions. This kind of attacks happen when the permissions are not well set, but they happen. And the final attack that I'm describing are directory traversal attacks, which the problem with these attacks are that web users are allowed to browse different directories of the web server which shouldn't be browsed. So the most common example is if a web server is not well configured and allows me to insert dots with slashes and go back into the directory tree so I could see all the files in the web server. This is a common way to describe them, but maybe we can find very difficult directory traversal attacks. So we can resume this with common principles of common injection attacks, which we have a user entering data into our application, and this data is not properly handled by the web application. So later, this data is used to execute operations behind the web application, for example, SQL queries inside a PHP application or HTML inside a PHP application. And the attacker can modify the input to alter the functionalities of the subjacent web application. So this is common to all the injection attacks. Yes? So to name some known attacks, we had multiple PHP-BB attacks on the last years. Vulnerabilities have been reported about this. Also popular CMSs have been compromised. The one we are testing today is an old version of a popular CMS because the vulnerability is already patched. And of course, custom corporate applications are compromised every day. So which are the threats we are facing with injection attacks? So without the proper checks, any web application can allow this kind of attacks. So this, the execution of these attacks can result in different kinds of problems. We can lose data. Our data can be altered or stolen. Our content might be compromised. Also, we would suffer of defacement in some cases. Maybe someone can use our site to pivot and attack another site. And of course, we can fall into private information theft. The problem is we don't have a silver bullet to prevent them, and I don't think we'll ever have. But we can think about tools or mechanisms to protect these kind of attacks. So to describe the anatomy of injection attacks, first the user enters the data into the web application, which runs inside an execution environment. In our case, when I'm presenting our tool, we will be talking about the PHP interpreter, but we have lots of environments like Java or ASP.NET virtual machines. So we can recognize 3 layers in these attacks. First, the information is provided by the end user. Later, this information, it's not properly handled by the web application inside the web application. So it's not aware of the malicious data that has been inserted. And at last, this information is used to perform operations which are designed for this web application, but they are specially crafted to alter the functionalities. So if we want to prevent or detect these attacks, we should do that in one of all of these layers. So, but sometimes injection attacks can get a little difficult. You say, well, if I look for SQL commands inside the user input, it should work. Well, sometimes we had to encode data in order to perform an attack. For example, when tampering get parameters, which are the ones that appear in the URL bar. For example, when trying to bypass string escaping, for example, web applications make use of some pre-designed functions to escape strings. And we can also want to exploit a third-party API, which may have a binary bug. For example, a precompiled extension in PHP. But the attack vectors change, but the vulnerable targets usually remain the same. We are talking about databases or to alter a browser's output. We can also talk about HTTP header injection or environment variables alteration. We cannot elaborate a complete list about of all these attacks and threats. So which are the common programmer workarounds? Well, first, a programmer might escape or encode and filter data provided by the user, but he can also fall into some problems. For example, if a programmer uses regular expressions to check the validity of the data, maybe he could forget about case. And if he's checking for only lowercase regular expressions, we could play with the case of the characters to bypass that check. Also, some languages allowed us to inject null bytes inside strings, and so the strings with a null byte will travel all inside the web application, and maybe if the library that checked for the validity of this data was a C-coded library, it would check until it reached the null byte. So if we put our attack after the null byte, maybe we could make an attack work also, even if the web application checks and thinks it's a valid input. So up to here, we described the threats we are facing. We've seen some known for some of you, some known threats and attacks. We described the anatomy of these attacks to generalize them. So now we are going to make a brief resume of the known tools that are available to address this kind of threats. Or maybe we should check the attack. Okay, I don't know if you can see. So the exploit retrieved the administrator username and the administrator MD5 hash. So now we will try to make this work, installing a grasp version of PHP. We will stay looking at the screen because it fails very fast, because it tries to retrieve one character and it fails, so the exploit fails. We start the web server. And try to execute the exploit again. So it starts testing for each character, and when it reaches 255, which is the last ASCII character, it returns. So it failed. The only thing we've done, we installed GRASP in an existing web server with existing web applications, and without modifying the web applications, we protected them. Now we continue with our talk. So now we'll talk about known tools to address these kind of threats. Some of them are only for detecting the vulnerabilities, and some of them are trying to block and detect ongoing exploits. We have automated source code analysis tools, which need the web application source code to analyze it. So depending on the technique, we can reach different levels of accuracy. And we must do this kind of analysis before releasing the web application, of course. So when these tools are run on a web application, we have to review all the alarms and see if we are in front of a false positive or false negative alarm. We also have scanners, which are black box testing tools, and analyze a deployed application and probe for non-vulnerabilities or have a fusor. But they mainly probe for known kind of vulnerabilities. Maybe if we are analyzing a custom-made web application, it's a bit difficult to detect some very, very difficult exploit. And they also have a high rate of false positives and negatives. We also have, in the firewalls and IDS and IPS category, some tools which work with signatures or must be trained with statistics. And they can also induce false positives and negatives. They usually don't detect specially crafted attacks. They look for patterns in input to warn about a possible attack. And they, of course, are susceptible to denial of service attack as their network counterparts. As a summary, some of these tools require an exhaustive review of all the alarms they raise. And we must confirm the false positives and negatives by hand. And we don't have evidence if we have sealed our web application because we are not sure if we have detected all the possible injection flows. So once we analyze a web application with these tools, we are not sure if we have sealed our applications from attacks. So now I will introduce the classical taint mode, which most of you should know about it, or may know about it. So it is a technique designed to address the problem of sending untrusted input to sensitive operations inside an application. It was first included by, I think it was Perl. But it only tracks data entered from outside the application, and when it reaches a sensitive function, it stops it. It's used mostly in development stages. They are useful for programmers to detect lack of checks in a web application, but in order to correct the errors, we must modify the application source code. We must add checks for each time we have an alarm. We must add a check in order to clear the mark. So in the previously described anatomy, we can locate this technique, this taint mode technique, in the third layer where the attack is being executed. So some programming languages have this protection mechanism in bundle, like Perl and Ruby. We have only two values of security for one string, which are untainted or tainted. They are useful for the programmer to check for the validity of the data that he is passing to sensitive functions. For example, here we have a Perl code snippet which retrieves a parameter called user. So in this line, the user variable is tainted, but if we check against it a regular expression, this is something useless, but it serves as an example. At this line, this variable becomes untainted. So the only thing we need to add is a simple regex check. Which are the pros and cons of these techniques? Think about this query here, this SQL query, where a username enters his username, and we check for the validity of this user. With a classical taint mode, this query would be fully marked as dangerous, even if this query is a totally valid query. So if we use this to detect ongoing exploits while an application is being run, we would fall in a lot of false positives and false negatives. This is because the string is treated as a whole and we don't have granular information about the composition of the string. But we could make use of this technique while in development stages. It's a useful technique, and it could serve as like a signal to. We should have a signal that whether if we checked or not the validity of the data. So, what are we talking about when we talk about character granularity? Let's think about instrumenting the string composition to add security data for each character inside a string. So the former query would look like this, with H meaning that that character is harmless and the D meaning that character is dangerous. So if we have control over each character in a string, we could make an analysis over the string and determine whether it's dangerous or not. In this case, although it has dangerous characters, it doesn't represent a threat to our application. So comparing these approaches, we have classical taint mode, which is useful while in development stages. While used in production or runtime, they may cause a high grade of false positives and negatives. And once we checked an application with a taint mode, we must modify the application in order to address the problems that were reported. One advantage is that it's already bundled with some programming languages, and we may use it without needing to install any extra software. We can find sensitive sources or sensitive functions quickly because every time a tainted data it's passed into a sensitive function, it raises an alarm. And of course, it's bundled with some programming languages. It doesn't have a high runtime penalty or memory penalty. With granular character information, we may use it both in development and in production. We have fewer false positives because we have more information about the string, about the string's composition. We also have more precision and per character information. And we can model vulnerabilities based on this granular information, allowing syntactical checks over strings. Of course, we are dealing with an increase of penalty in memory and runtime, which we'll discuss later. So now we made a brief description about the threats, a technique to identify or to track information inside a web application, which we will use it for designing our solution. And, now we will locate our solution in a very basic schema of a web applications architecture. Imagine if a person reviews all the data entering a web application or leaving the web server, deciding whether if the data is dangerous or not for its output or for entering the web application. And when the data enters the web application, he marks it as dangerous because it's been provided by an untrusted source. We can also locate this person on the three bullets which are painted And this person can also watch if the data being passed to a backend server, for example, a database server, it's dangerous for its execution. And he also could mark data incoming from the database server. For example, if stored HTML code is being retrieved from the database, he could see if this code could result in a cross-site attack, for example. So he would know if this data is dangerous for the application to be used by the application. So GRASP is located in these three layers. The first layer, which is between the web server and the outside world, marks all incoming data from untrusted sources and prevents harmful data from being output to the outside world. And there also privacy policies are enforced, which are defined over the data. The second layer, which is inside the execution environment, tracks all the information which was marked at the beginning, at the first layer, and it tracks all the flow of the information inside the web application. The third layer, which is located between the web server and the backend servers, checks outgoing data for attacks. It also checks for incoming attacks, which may be, as I said, dangerously formed HTML code. And it also enforces privacy policies and marks all incoming data from databases as untrusted. So the design principles we followed was we would modify for each language the way any web application receives, handles, and outputs data in order to prevent injection attacks. The security information is tracked inside the web application's execution environment. As I said, we use a technique of character granularity information. And we will classify data operations and functions into three groups. The first one are sensitive sources, which are the functions or the places where data is entered to the web application and should be considered untrusted because they form attack vectors to our web application. We also define sensitive sinks, which are functions or modules where we have to check the data we are supplying them in order to execute some operations. And data manipulation operations are those in which we must handle this security data and propagate the security information of the data inside the web application. So each of these operations must be modified to be security aware. So as an architectural description, for each programming language, we modified its execution environment, augmenting it to add additional information about security over the strings. And we can identify possible sensitive sources at get, post variables, for example, environment variables such as HTTP headers, cookies or session variables, and incoming database data. Some possible sensitive things which we have to be aware of are queries sent to the databases, of course, data received from a database which will then be output to a user, for example, to protect cross-scripting attacks. All these attack vectors, which can be controlled by an attacker, must mark the information as dangerous because we later can use it to perform a sensitive sync operation. Of course, security data is propagated among data manipulation operations. So how do we protect? Well, we decided to implement the protection over sensitive things with finite state machines, which was a technique that resulted for us. We may choose another technique. So having this granular information about strings, we could analyze them with these finite state machines and state whether a string is would be dangerous for our application to execute it. The important thing about this is that this protection is deterministic for each family of vulnerabilities. For example, we design finite state machines for protecting SQL injection attacks, another finite state machine for protecting against cross-site scripting attacks. So inside a web server, the protection against the attacks is the same for all the web applications. And we don't have to modify the web application for that purpose. Here we have an example of a finite state machine. I don't know if you can read something. Here we have a query with an attack, a simple attack. So we start here at this state, and each time a character is read, we follow into a transition. For example, every time we take a character with mark harmless, we stay in this state because there is no arrow for going out from this state without when analyzing a character with harmless mark. Maybe we should add here a loop arrow. But when we reach this, But when we reach this quote here with dangerous mark, the machine transitions to this state, which is a quote with this here. Well, I can't find it right now. Oops. Well, it transitions to another state. Here, in the first quote, we have a not marked quote, so the transition is made to this state with a quote without a mark, and then we have another quote with dangerous mark over it. So when it reaches a dangerous quote with a mark that closes a safe quote, it reaches the attack state. Well, here we have different kinds of identifications. We base this finite state machine on MySQL's lexical analyzer. So it protects against SQL injection this way. So which are the security features of our system? Injection attacks are detected and can be prevented or blocked. Every web application which is in the web server we are installing the protection system is protected immediately. A finite state machine checks for cross-language boundaries, which are these places where SQL, for example, SQL queries are made inside PHP applications or shell command injections. All attacks are logged, and we can define if we want to block them or not. And we don't need source code modification or ad hoc checks. In privacy meanings, we can define privacy policies over data and describe how a system should manage that data. A privacy officer could define the privacy policies over the data, and the sensitive sources tag information accordingly to these privacy policies. Sensitive things enhance privacy and make sure that those policies are enhanced. Data manipulation operations also propagate these tags, these privacy tags. And the data inside the execution environment always have a privacy tags associated. For example, let's say a database stores credit card numbers from users. So this data should never be sent out to users, or for example, we could define a policy that states data from this column should never be printed, or data from this column should only be printed to its owner. That's an example of a privacy policy. So when a database, when a web application sends data to the end user, this policy must be enforced in order not to fall into a privacy violation. So, as a summary, these ideas can be directly implemented for PHP. We developed a prototype, which we have seen a demo, which is a modification of the PHP interpreter. We choose PHP because we had the source code available, and there are lots of PHP vulnerabilities reported each day. So we distribute this as a patch for the interpreter. The installation requirements are the same as the installation for a regular PHP interpreter. We don't need special tuning or training, and we don't have to modify the source code of the web applications that are being protected. So now we'll talk a little bit about the prototype itself. We'll discuss covered functionalities and implementation details. We'll go deeper inside PHP internals, not a lot, and make an architecture description and enumerate the modifications we made. So this prototype is implemented for the latest version of PHP, which is 5.23. But we've been working on this technique since PHP 4. It implements all sensitive sources, so it marks all incoming data from get, post, and cookies variables. We have only implemented one sync protection, which is SQL injection for MySQL databases. The string manipulation operations were modified to propagate marks, except regex. We couldn't make it for this talk. We have implemented an optimization for the marks, so we don't have double space while storing marks over strings. For example, if we have a whole string marked as dangerous, we only store a small amount of data, which I will show you later. We have source code available to download in this website, which I invite you to visit it. And we are willing to build a community around this in order to continue developing this prototype. So, while talking about the execution environment in PHP, we must modify the data, how the data is stored inside the web application. So we can recognize the main data structure inside PHP interpreter are zvals. They store every value and intermediate values while the application is being executed. So we had to modify this structure. This is the main struct of a zval, which is composed by the value, which is a union. This is the main structure of a zval. And we added a segmark. This is also, of course, this is not the whole source code. It's like an illustration of the modification. So we have a char pointer to store the information about strings. So when we are trying to store a string, we store this value, which is a null pointer, to represent that string has full safe mark. When talking about a full dangerous string, we store this pointer. And when the situation is a mixed situation between dangerous and harmless characters, we store an array of bytes, which with each byte representing this character mark. This is, of course, this allows double space for all the strings inside a web application. We only have double space when we have mixed mark situation. So the sensitive sources we implemented, we modified, are the get, post, and cookies variables, which are marked as dangerous by default. As I said, we implemented the MySQL module to implement protection against SQL injection attacks, which was the finite state machines which we saw. And every time a SQL query is sent to the MySQL module, it's checked with this finite state machine and checks if it's an attack or not. We can configure if this would be blocked or not. We have modified the string operations in order to preserve these marks. Zevals are initialized with safe mark by default, unless we are talking about a get post on cookies retrieve data. And the propagation allows us to track the user control data inside the web application. So to enumerate the modifications we made to this interpreter, we were focused in main data structures such as Zevals, which I mentioned, and smart strings, which are a secondary structure used to store strings and make operations over strings. Basic strings operations such as concatenation and the basic functions were modified. All the macros that are used to construct Zevals were modified also. Get, post, and cookies are initialized with dangerous values, dangerous marks. And of course, we had to modify some execution environment files in order to make this work. And of course, the MySQL module to implement the protection against SQL injection. So we test our prototype with popular CMS and also database management systems or interfaces, and of course with home-built applications. So at the beginning, now it showed a 20% increase in runtime, which should be lowered. We tried to exploit known vulnerabilities against known applications, and we had been successful while protecting them with GRASP. We added some regression tests to the PHP ones in order to test the implementation. And memory was increased in 30% due to SecMar allocation. We can compare it to other protection mechanisms such as IDSs, which also add runtime penalties. But we must say that these penalties can be lowered. So going deeper into the prototype, although it's very transparent for the developer to use this protection, we added some functions to interact with marks. For example, we had marks to set the full dangerous mark to a string. Also, we have a function to clear the mark of a string and to retrieve and print, for example, the mark of a string. These are bundled with the PHP basic functions, so any user which is using a modified PHP interpreter can use them. For example, if the user is certain he's sanitizing the data, he could clear the mark of a variable on his own risk, of course. And we can also want to allow SQL commands written by end users, for example, while we are developing a database interface, administration interface. So these functions are also useful for those purposes. We have a few configuration parameters which are included in the PHP ini file. We can define if we want to block SQL attacks or only to log them, and to log all the queries with all the marks in a log file. We can turn on all these parameters or combine them anyway. For example, a log file in GRASP should look like this. This is the time where the query was made. Of course, in this first prototype, we have only MySQL protection, so I'm showing a SQL query log file. So here's the IP where the attack came from, and we have the file in the web server where the attack took place. And we have the query which was executed. And when we watch this log file and we see a dot underneath a character, it means that character is safe and has a safe mark. And when characters are repeated, it means this is a character which has a dangerous mark. So we can easily see how the attack was performed. We also added like the PHP info function, but for Grasp, which shows us the configuration parameters and the percentage of attacks which were made against the web server, and also details against how many attacks had each file inside the web server. This is the usage of this function is the same as PHP info, which you call it and it prints this information. So we are distributing this as open source software, releasing it under Apache 2 license, and we hope a lot of people can join us and continue with this work. We have a lot of work to do, which we are talking. I will talk some things about future work now. We have remaining attack vectors to be implemented, such as cross-site scripting and other attacks. We must implement full privacy protection and polish, of course, the current implementation of Grasp. We should make some optimizations to allow high performance. And we have also talked, for example, with Vit7Emma to build a classic taint mode and a common framework to allow Grasp to act as a classic taint mode and as a precise protection system. So maybe we can follow that line. We can also think about per-page protection policies. For example, defining for each web page inside a web server a different protection policy. This could allow an administrator to turn off the protection for certain files in the web server. We also, of course, we thought about different levels of marks. We could mask in 1 byte 8 different marks, or even 2 to the 8th different marks, because we have 8 bits to encode a mark. And we also thought about different implementations for different languages, for example, ASP.NET, and we thought about modifying, for example, wrapping the native string classes or changing the class loaders, but because we don't have the source code for those languages, so we could have to make a different approach for this solution. So you have further material on Grasp. You have an included paper in the conference material, and also we had a paper published a year ago about its privacy features. So I invite you all to go to the web page and download the source code and test it and play with it. And we also have a discussion mailing list, which we are trying to build a community around it, and everyone is invited to collaborate. And, well, thank you.